Hello everyone. Welcome to episode 5 in my op-amp tutorial series, lab demonstrations for episodes 3 and 4. In the previous episode, we introduced the integrator and the differentiator op-amp circuits. If you haven't had a chance to watch the previous episodes, you can check them out on my channel. Now that we've done formal introductions and analysis for some of these op-amp circuits, it's helpful to see them in action. Today we'll look at lab demonstrations of the resistive non-inverting op-amp configuration, the resistive inverting op-amp configuration, the integrator circuit, and the differentiator circuit. Here is the schematic for the non-inverting amplifier as seen in episode 3 of the series. Now we'll set the resistors to specific values and plug a function generator and oscilloscope into the circuit. I've configured the circuit to have a gain of about 4.03 volts per volt, which is high enough to be good for a lot of circuits, but low enough for the op-amp to behave in an ideal manner. Trying to pull too much gain from an op-amp causes issues we'll discuss once we discuss the gain limitations of op-amps. Vs is provided by a function generator. The function generator has about 50 ohms of source impedance of its own, and I've put a 10K resistor in series with it, so the source resistance is about 10.05 kiloohms. At first, channel 1 will be in the right position, measuring V in, then we'll move it to the left position, measuring Vs to see if there's a significant difference. Channel 2 is on V out. The power supply rails are approximately plus 12 and minus 12 as usual. I won't measure them today. It won't be important to know their exact values so long as we remain far from them. So here we have the circuit breadboarded and with the scope and function generator connected up to it. I now enable the function generator's output at 100 Hz. Here we have the scaling factor for the input signal on channel 1 and the output signal on channel 2, both set to 1 volt per division. The input voltage peak to peak is about 1 volt, with the output voltage at about 4 volts. This is our expected gain of 4. It is currently set up with the input voltage moving right around 0 volts, but if I increase the offset voltage generated by the function generator, we can see the effect of the offset being amplified by 4 in the positive direction, and if I decrease the offset voltage generated by the function generator, we can see the effect of the offset being amplified by 4 in the negative direction. The measured gain is about 3.8 on the scope right now. If we increase the frequency to 500 Hz, we see that the gain remains about the same. So it appears to be approximately flat over frequency as designed, though this will of course break down eventually due to op-amp non-ideality, but we won't study that effect today. Similarly, we can run different waveforms through it, which add additional frequency content depending upon the shape of the waveform. Here we have a square wave. There's little degradation of the gain here. That's likely due to non-idealities in the LM324's frequency response, as square waves have high-frequency components. Here we have a triangle wave, which has very close to the same gain as the sine wave, as expected. Triangle waves don't have as much high-frequency content as square waves. And we go back to our sine wave. So over these tested frequencies, the ideal op-amp derived gain appears to hold. The non-idealities come into play at these apparent low frequencies because those different waveforms have high-frequency content. So note that even low-frequency waveforms, if non-sinusoidal, are subject to effects at much higher frequencies. This is especially true of square waves, as they have very sharp edges. Now I move the channel 1 scope probe to its second position from the schematic so that it's directly on the op-amp non-inverting input. This is to test if the 10K resistor we put in series affects the gain of the circuit at all. And as we can see, the resulting waveform looks the same and has the same 1 volt peak-to-peak value it had before. This is the expected result, as in the ideal op-amp, the input currents are 0. And so even with a fairly high impedance of 10K, the op-amp drops negligible voltage across the resistor, making it a good candidate for buffering a weak signal. Moving the scope probe position back to where it was before, we now test what happens if we unload the output of the op-amp to see what kind of output impedance it has. And as we expect, the voltage output does not change. So the LM324 behavior appears to match up fairly well with the ideal non-inverting op-amp circuit, with our spot check test at 100 Hz. Now we move on to the inverting amplifier configuration. I've set it up with the same gain setting resistors as with the non-inverting amplifier configuration, which will produce a gain of about 3.03 volts per volt, which is 1 less than the non-inverting amplifier configuration. Channel 1 of the scope is on the V-in point on the left side of the 3.3K resistor, and channel 2 of the scope is on V-out. Now, while the 50 ohm source resistance of the function generator will affect the gain from Vs to Vout, it will not affect the gain from Vin to Vout, as the gain reduction from the 50 ohm resistor will be effectively compensated for because we measure the input at the Vin point. Here we have the inverting amplifier configuration with the oscilloscope and function generator connected. I now enable the function generator at 100 Hz. We see that the input is about 1 volt peak to peak, and the output is about 3 volts peak to peak, which is the gain of 3 we expect. We also note that the output is 180 degrees phase shifted from the input, which is expected from having a negative gain. Now, when we change the input to a square wave, the output appears to be a square wave with the same phase shift at all frequencies and a similar gain, slightly attenuated due to non-idealities. A triangle wave produces similar gain and the same phase shift. Moving back to a sine wave, we now look at what happens at higher frequency and note that the gain stays the same as expected. Going back to 100 Hz to check the effect of the output resistance, we see that removing the output resistance has a negligible effect on the output waveform. And finally, we examine how the offset adjustment changes the output. Increasing the DC offset of the input causes the output to become lower, and decreasing the DC offset of the input causes the output to become higher, as expected. Now that we've covered the inverting amplifier, we'll move on to the integrator circuit. Here we have the general circuit for the integrator with the feedback resistor. And now with R2 set to 3.3K and three 470 nanofarad capacitors in parallel to make the 1.41 microfarad feedback capacitor. Similarly to the non-inverting amplifier, we connect oscilloscope channel 1 at the Vin point, thereby eliminating the effect of the function generator's source resistance, and we measure Vout with scope channel 2. I've removed the feedback resistor for now to show how difficult it is to deal with an integrator without one. So here we have the circuit breadboarded, and with the scope and function generator connected up to it, I now enable the function generator's output at 100 Hz. Here we see the input signal on channel 1 set to 200 millivolts per division, but the output on channel 2 is nowhere in sight. Here I spend an obnoxiously long time trying to get channel 2 signal in range, demonstrating the problem with using a pure integrator without the feedback resistors. The offset voltages, in spite of being small, get gained up very high by the pure integrator, and therefore, when they drift around a little bit, it makes it virtually impossible to set the offset voltage precisely enough to get the output within a reasonable voltage range. So here's the modified schematic with a 100K resistor in the feedback loop to limit the gain at low frequencies. The point of transition between integrator and fixed gain is about 1.129 Hz with these components, and the maximum gain is set to 30.3 volts per volt. This means that so long as we operate at about 11.29 Hz or higher, the circuit will perform like a proper integrator, so our starting frequency of 100 Hz will work fine. Since this circuit has different gains at different frequencies, we'll derive the gain for a frequency of 100 Hz so we know the gain there. And then we'll move up and down in frequency to see the changes from that 100 Hz baseline. At 100 Hz, the gain is about 0.3421. The fact that the value is purely imaginary indicates that the phase is 90 degrees off from the input voltage waveform. Coming back to the test setup, here I install the 100K resistor in parallel with the capacitance as shown in the diagram we just looked at. And now, channel 2 is much easier to center on the screen. Looking at the phase difference between the two waveforms, we see that the output is leading the input by 90 degrees. This is due to the pole in the transfer function. In fact, it's best to think of it as an amplifier that inverts, introducing a 180 degree phase shift, and then adds 90 degrees of lag to the output. This makes it look like it's just leading the input by 90 degrees, but it's really lagging the input by 90 degrees and being negated. A 90 degree lag is what we expect from a pole when the frequency is much greater than the pole's corner frequency, which in this case is 1.129 Hz. Since our current frequency is 100 Hz, that is indeed much higher than 1.129 Hz. The input voltage is sitting at 424 millivolts peak to peak, and the output is at about 164 millivolts peak to peak. This is roughly a gain of 0.387, which is close to our expected gain of 0.3421. There's a fair bit of noise, so that produces some error in the peak-to-peak value. Increasing the frequency to 500 Hz decreases the output voltage further by approximately a factor of 5, corresponding to the factor of 5 increase in frequency, though the peak-to-peak noise on the scope is corrupting the measurement, so we don't see the volts peak-to-peak on channel 2 precisely decreased by a factor of 5, but it's close enough given our component tolerances and test setup. Starting back at our 100 Hz baseline, if we then drop the frequency down to 10 Hz, we see the output voltage increase by about a factor of 10, corresponding to the factor of 10 decrease in frequency. Moving back to 100 Hz, now we change the wave shape, and we see that when the input is a square wave, the output is a triangle wave. This is exactly what we expect because a triangle waveform is the integral of a square wave. Finally, with a triangle wave, we see the integral of a triangle wave, which looks similar to a sine wave, but it's really two parabolas, one concave up and one concave down, that are joined together to sort of look like a sine wave. Moving back to the sine wave, we see that moving the offset very slightly will cause dramatic changes in the output because DC is the maximum gain point. So even though we've mitigated that issue with the 100K feedback resistor, it is still present to some degree, the high gain at DC. Now we remove the output load to see if that affects the output. And as we expect, there is no change in the output when we unload the circuit. Finally, we get to the differentiator with source resistance. Here I've set up the differentiator with a 1.41 microfarad capacitor from before and 10K feedback resistor. The 100 ohm series resistor will cause the gain to stop increasing at about 752.5 Hz. That is gain from the source voltage, not the input voltage. The maximum gain will be capped at 66.67 volts per volt as a result. The main frequency we'll look at is 10 Hz, so I derive the gain at 10 Hz, which is about 0.8859 or close to 1. Going higher than this frequency will increase the gain, going lower should decrease the gain. Powering up the function generator, we see that at 10 Hz, the input voltage is at about 760 millivolts peak to peak, and the output is at about 660 millivolts peak to peak. This is around 0.87 gain, which is close to our expected 0.8859 gain. Note that there are significant amounts of high-frequency noise on the output. This is because the differentiator amplifies high-frequency content more than low-frequency content. This will tend to make gain determinations more difficult, since I'm looking just at the peak-to-peak voltage, and so the noisier the signal is, the more that peak-to-peak voltage is actually contained in the high-frequency noise, rather than the amplified sine wave signal. Here, the output voltage appears to be lagging behind the input by 90 degrees, the opposite of what happened in the integrator circuit. Recognize, however, that as this is due to a zero, what we're seeing is actually the output leading the input by 90 degrees, in addition to being inverted, resulting in the apparent lag. At 5 Hz, the output voltage has dropped to 384 millivolts, which is not quite as much of a decrease as our prediction, but it's pretty close, and the difference is likely just due to noise riding on top of the signal. At 50 Hz, we see the output voltage has risen to 3.08 volts. This corresponds to a gain of about 4.01 volts per volt, which is close to our expected value of about 4.43 volts per volt. The components I'm using, again, are not very precise, and neither are oscilloscopes in general, so the errors we're getting are not unexpected. Back to 10 Hz, we explore the effect of changing the offset voltage up and down. We see that increasing the offset voltage results in no change in the output voltage, and decreasing the offset voltage similarly results in no change in the output voltage. This is because the circuit is entirely AC coupled through the input capacitor, and so the DC voltages from the function generator are completely removed, and only the AC signals get through. Changing the input to a square wave produces what we expect from the derivative of a square wave. The op-amp outputs voltage extremes at the square wave transitions because the sharp edges of the square wave translate to a very high derivative of voltage with respect to time. The op-amp rails during these transitions because the derivative is so large. Changing the input to a triangle wave produces a square wave, which is the expected waveform since a square wave is the derivative of a triangle wave. An interesting note, the noise on top of these square waves is actually related to, the shape of that noise is related to the differential nonlinearity of the DAC inside my function generator, because the function generator is a DDS function generator. And so you can kind of sort of see where the differential nonlinearity is higher. This is easier to look at if you increase the gain and if you try to get rid of some of the noise, choose the frequency properly. But it's kind of interesting that you can see this when the function generator is outputting a triangle wave. Moving back to the sine wave, we're going to take a quick look at what happens when we remove the 1K output load and see if it has any effect on the output, as we've done for previous circuits. And the removal appears to have no significant effect, so we put it back in. That concludes this episode. Today we did lab demonstrations using the LM324 for the resistive non-inverting and inverting amplifier configurations, as well as the integrator configuration and differentiator configuration. These circuits were introduced and their transfer functions derived in episodes 3 and 4. Next time, we'll be introducing summing amplifier circuits, specifically the inverting and non-inverting summer circuits, and deriving their transfer functions. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave them in the comments. See you next time.